Okay, this is still Unit 1, Matter and Measurement, and this is Lesson 2. Tonight, you will learn the difference between physical and chemical changes, and you will understand how to tell the difference between elements and compounds. And then lastly, we're going to discuss the various techniques used to separate matter. So what's the difference between a physical and chemical change? Matter's always changing. Ice in your drink melts, wood in the fireplace burns. Well, a physical change is a change that does not alter the chemical properties of a substance. For example, cutting paper. If I cut a piece of paper into a bunch of little pieces, I still have paper. Also, a phase change. If I take ice out of the refrigerator and I put it in a bowl, it will melt. I still have water. I just went from water solid to water liquid. So a physical change is a change in the size or shape. It is the same material in a different form. It looks different, but can go back to the original state. And most important, no energy is produced as a product. So here we're showing ice going into water. This is a phase change, and it's called the process of melting, which I'm sure you're all familiar with. Cutting paper, I still have paper. Now, how does that differ from a chemical change? A chemical change is a reaction in which the composition of the substance is changed permanently, like rusting. If I take a can and I leave it outside for a very long time, it'll rust, and it'll get to the point where it'll disintegrate and fall apart. I can't get my shiny can back. The properties are not the same as the original matter. And in this case, energy is produced. And it's usually produced in the form of light, fire, or heat. So both of the demonstrations that I did on the first day of school were also examples of chemical changes. When wood burns, all that's produced is carbon ash. I cannot get back my original piece of wood. I want you to take a moment and pause me, and I want you to determine whether the following changes in matter are chemical or physical. You can just put a P for physical and a C for chemical. So pause me now, fill them out, and then check your work. So hopefully you've done that. Burning toast, chemical. I can't get back my toast. Making ice cubes, physical. Burning a candle is chemical. Spoiling of milk, definitely chemical, can't get that back. And making jello. Jello is physical. It goes from a liquid state to a solid state. So hopefully you scored a 5 out of 5 on those. Let's move on to the next objective, the difference between elements and compounds. We're going to circle all of the elements and underline the compounds below. On the line provided, record the number of different symbols within the species to the left. So this has two different symbols, a carbon and an oxygen. They're both capitalized, so this is 2, and it isn't compound. This has a C for carbon, H for hydrogen, O for oxygen, and another H. But H is the same element, so we're going to put 3. It's got 3 different symbols. and this is also a compound. The first one was carbon monoxide. You'll learn how to name these. This one is ethanol. The next one is sulfuric acid, and it's also a compound, and it contains 3 different symbols. Oxygen is an element. It's a diatomic element because it's 2 of the same atom, and it has 1 symbol. Carbon is an element. It has 1 symbol, and it's a monatomic element because it's only 1 atom. Magnesium is also monatomic. It's an element with 1 symbol. Aluminum cyanide is aluminum, carbon, and nitrogen. It's a compound, and it has 3 different symbols. Helium is an element. It is 1 symbol. H2O is water. It's a compound, 2 different symbols. Copper is an element with 1 symbol. This is cobalt. It's a big C with a little o. This is an element, 1 symbol. This is chlorine. It's an element. It's also a diatomic element, and it's got 1 symbol. This is nitrogen triiodide. It's a compound, and it has 2 symbols. This is sodium chloride. It's a compound with 2 symbols. And this is just iodine, but it should be I2. So please add that in, because iodine is one of Brinkelhoff or the 7-Up. It's diatomic, and it has 1 symbol. So let's answer some questions. Does each compound have the same number of symbols? Well, let's look at things that we underlined. This has got 2, 3, 3, so no, they don't. For each element above, how many total symbols are listed? Well, each element only has 1 symbol. What is the minimum number of symbols that must be present in order for a species to be considered a compound? Well, remember, a compound is 2 or more different, so the minimum number is 2. So let's write a formal definition of an element. An element contains only 1 symbol and elements cannot be broken down. A compound contains 2 or more symbols and compounds can be broken down by chemical means. Okay, I'll give you a minute there to write that down. Okay. We have to understand compound formulas. When we look at a compound, we have to know how many atoms of each element are in the compound, because we need to be able to calculate its mass. And the mass is based on the number and types of atoms that are in a compound and adding them all up, respectively, according to their masses. So, when we look at a compound, you may see a subscript. The subscripts tell you the number of each type of atom that is present. So for the first example, let's just use CO. This is carbon monoxide. We have one carbon and one oxygen. If I were to do CO2, I have one carbon and I've got two oxygens. If there are parentheses present around two or more atoms, the subscript applies to all atoms within the parentheses. It's kind of like the distributive property of math. So if I have AlCN3, I have one aluminum. I have C, but there's three of them, so that's 3. I have an N, but there's 3 of them, so 1 times 3 is 3. I have 3 N's. And lastly, if one of the atoms within the parentheses has a subscript, you multiply this number by the number outside the parentheses. So in the example, Fe2SO4 3, which is iron 3 sulfate, I have 2 iron. Sulfur, I have 1, but there's 3 of them, times 3 is 3. My oxygen, I have O4, so there's 4 oxygens here, times 3, so I have 12. So we have to be able to determine the number of atoms in a compound. So if I wanted the total number of atoms, I would add things up. So for these two, I have 3, and 3 is 6 plus 1 is 7 total. For this one, I have 12, and 3 is 15, and 2 is 17. Sometimes the Regents will ask you for the total number of atoms in a compound. Rules for writing element symbols. Very simple. The first letter is always capitalized. And then the second rule is if there is a second letter, it's lowercase. Okay, these are a list of the most common. Something happened here. Oh, I see. These are done twice. Okay, so we can put a line through these. Maybe on your sheet it's not. There we go. Okay, these are a list of the most common elements and their symbols, and you have to learn these. I will put them on Quizlet because there will be a quiz on them a week from Friday, September 20th. So you're going to look for these on Quizlet.com, but even easier, I will put the link by this Friday in our Chapter 1 notes, and it'll say element names and symbols. All right, let's move to our last objective. How can we separate matter? Well, there are a couple of ways. First one is filtration. This is a physical separation. This is where I have a funnel with a piece of filter paper and I pour whatever it is that I want to separate through the filter paper. It separates undissolved particles from the liquid. So what happens is undissolved particles get trapped by the filter paper. The filtrate, which is the liquid, filtrate is called the liquid, flows through. And a great example of this is a mixture of sand and water. So if I have a beaker of sand and water and I pour it through the filter paper that's being held by the funnel, the water will flow through into the beaker. The water would be called the filtrate, and the sand gets trapped in the filter paper. This type of physical separation, filtration, will separate heterogeneous mixtures. And this was an example. So heterogeneous mixtures, those that are not uniform throughout. Let's move to the next one. Here we have two different types of things. We have an evaporating dish, which is like a little white porcelain dish with a watch glass over top so things don't spatter. And here we have a crucible, which is a smaller porcelain dish with a little cover. Both of these are physical means of separation. And what we can do is in both of these cases, separate what's called the solute, which is the dissolved solid, from the solvent, which is the liquid. By boiling, to complete evaporation. So, a good example of this is salt water. The salt that I dissolve in the water is the solute. The water is the solvent. And if I heat it till complete evaporation, the water escapes. Okay? So the solvent escapes and it turns into a gas. And what's left behind is the solute or the salt. So this is used to separate homogeneous mixtures, those that are consistent throughout. And an example here would be salt water. Okay, we only have two more and we're done. Distillation. Distillation is also a physical separation. And it separates the solute from the solvent by boiling. And then recondenses in the receiving flask. And I'll explain this to you. So this is important because it is separation based on boiling point. So this is for homogeneous as well. And a good example of this is Listerine. And I'm going to explain that. So, over here in this flask, I would have my Listerine. Okay? And Listerine is made up of alcohol and water. So as I said, Listerine's made up of alcohol and water, and alcohol has a lower boiling point than water. So as this substance is heated, the alcohol will vaporize first and travel through this tube. And there's an inner tube and an outer tube. And we have cold water flowing in this end that's hooked up to a sink, and cold water flowing out this end. And as the cold water circulates the inner tube, it changes the alcohol that's turned into a gas back into a liquid, and then it comes out here. And then if we kept heating, then eventually we can get the water to come over in the same fashion. Okay, let's go through the last one. Chromatography. You should have done this in living environment. This is also physical, and it separates based on size, molecule size, and solubility. And it separates the pigments or the components of a mixture based on molecule size. So the lighter something is, the further up it will travel, and based on its solubility in the liquid. And this is also used for homogeneous mixtures. And an example of this would be ink in a pen. On the other hand, chemical separation requires reacting a sample with something else in order to turn it into a completely different compound. Okay, that's it for lesson 2. See you in class on Friday.